started with our next speaker. So our next presenter is Matt Kramer, who is part of the DUNE collaboration and is going to be telling us all about that. Okay, everyone see the slides? Okay, right. And thanks so much for being here, Matt.
My pleasure.
And you should just be able to use the, I think this is working, like if you just press up. Yeah, should work. Does it work?
Right and left.
Right and left?
Right and left.
There we go.
There we go.
Okay.
Yeah. So I'll be talking about DUNE, the Deep Underground Neutrino Experiment. We've used NERSC in the past and the recent past, as well as the ancient past, and what we look forward to in the future. So before we get into NERSC, let's talk about DUNE, because I assume most of the audience has only a vague idea of what a neutrino may be. So what are neutrinos? The short answer is we don't know either, but what we do know is they're these mysterious fundamental particles, at least they appear to be fundamental particles, that are a little bit more difficult to study than some of the more familiar ones, mainly because they're very ghostly. You can send neutrinos through like a light year of lead, and depending on their energy, they might not interact at all as they travel that distance. So that's the sort of challenge that we're dealing with when it comes to neutrinos. This weakness or this ghostliness comes from their lack of electric charge. Without gravity, all they do is participate in the weak interaction, which is weak, like you might infer. So one example of a reaction that produces a neutrino is nuclear beta decay. In that reaction, a neutron decays into a proton and also kicks out an electron. And accompanying that electron is an antineutrino, an electron antineutrino. And that balances out something called electron number. And neutrinos help with that balance. So you see that the electron has a corresponding electron neutrino. And there are also two heavier siblings of the electron, the muon and the tau, and each of those have a corresponding neutrino as well. So we say that there are three so-called flavors of neutrinos, the muon, the electron, and the tau neutrino, or not necessarily in that order. And the strange thing about them is that if you take, say, an electron neutrino, it turns out that it's actually a combination of a light neutrino, slightly heavier neutrino, and an even heavier one. So we can talk about neutrinos either in terms of their flavors, or we can talk about them in terms of their masses. And if we take something that's a definitive flavor, we find that it's actually a combination of three different masses and vice versa. And this leads to the phenomenon of neutrino oscillations. And the observation of those is what allowed us to determine that neutrinos are not massless, which was one of the first big breaks from the standard model of particle physics. So we're still studying this phenomenon and continuing to discover new things about neutrinos. But one of the nice things about working with neutrinos is even though they're hard to detect, they're all over the place. They come from the sun, they come from atmospheric cosmic rays, they're produced in the core of the Earth, come from nuclear reactors, and in DUNE's case, they're going to come from particle accelerators, as well as hopefully a supernova. But like I said, they're really hard to detect, so you need really gigantic detectors, and that's one of DUNE's challenges. So anyway, I've talked about neutrinos and a few of their properties, but why do we even care about these? Besides the fact that they're just inherently interesting if you're a nerd like we are. But since they were detected in 1956, we're still figuring out how they behave and their properties. We know that they have three masses, but we don't know if we have one light one and two heavy ones or vice versa. We don't know what the absolute scale of those masses might be. We know the differences in the squared masses because oscillation tells us that. But we can shift the three masses up and down a scale while preserving these mass square differences. So we don't know what that absolute offset is. We know the misalignment between the mass states and the flavor states, this superposition that we see here. We know the size of that, and that's expressed in terms of these so-called mixing angles. But we could measure them more precisely. And if we do, we might find inconsistencies in the model, and that could point to new physics. And finally, one of the big questions about neutrinos is whether they violate the symmetry known as charge parity. So if you take an interaction, you flip the charges on all the particles, you also reflect that whole movie in the mirror and then play it again, does that new movie also obey the laws of physics? If not, then neutrinos violate charge parity or CP. And one implication of that would be that antineutrinos and neutrinos behave differently from each other. We know that quarks do that a little bit, but not a whole lot. And the imbalance that we see in quarks is not enough to explain why in the Big Bang we got more matter than antimatter. Neutrinos could help answer that. So that's one of the things that DUNE is mainly looking for, is this CP violation phenomenon. And it turns out it's really hard to measure, which is why we need to build an experiment like DUNE. Finally, there's also the question of whether neutrinos and antineutrinos are actually different faces of the same particle, maybe different behaving faces, but still the same particle mathematically. That would make them a so-called Majorana particle. And if that's found to be the case, then neutrinos would be the first known particle to have that property. DUNE is not able to measure that or to look for the Majorana nature of the neutrino, but other experiments, neutrinoless double beta decay experiments, are working on that. Finally, just going beyond particle physics, fundamental particle physics, neutrinos can also tell us a lot about what goes on deep inside stars because they emerge without scattering nearly as much as, say, a photon would. Similarly, a supernova explosion we'd learn a lot about one of those if we could look at the neutrinos from one. So anyway, DUNE, I'll finally talk about DUNE now, is it's an international but US hosted experiment that aims mainly for CP violation in the mass ordering, like I just mentioned. It also wants to get better precision on the mixing parameters. It wants to hopefully observe neutrinos from a supernova if we're lucky, and also just search for general signatures of physics beyond the standard model. And so in order to achieve these goals, there are three key ingredients. There is a very intense neutrino beam produced at Berkeley Lab. There's a near detector close to the beam, and it must be designed to handle the intense beam and measure it before it oscillates, so that we can then compare that to what we see in the gigantic far detectors, which will be placed about 800 either miles or kilometers, I can't remember right now, away in South Dakota, deep underground in a gold mine, about a mile underground. And so with that combination, we can get the parameters we're looking for, hopefully, if nature is kind to us. But where does it all begin is in the beamline. So we start with protons, we accelerate them in some rings, we slam them into a target, we get particles called pions. Those are focused by magnetic horns and then directed into a pipe where they decay. And finally, when they decay, we get muons, which we don't care about here. They just slam into the wall, and we get muon neutrinos, which then travel 1,300 kilometers through the Earth. Now I'm getting it right, to South Dakota. So that's how we make our neutrinos, and this is how we detect them. The technology that DUNE uses is called the liquid argon time projection chamber. You can't time travel with it, but you can take nice pictures of particle interactions. So the way it works is that particles will travel through the liquid argon. As they do so, if they're charged particles, they will leave a trail of ionization in their wake, electrons and ions. And then there's an electric field inside the liquid argon that will drift the electrons toward a plane where they will be read out. You could use wires, like in this illustration here, in which case you have to sort of homographically reconstruct the 3D coordinates of these hits. And by the way, the time is what gives you the third perpendicular dimension, the so-called drift dimension. So you could use wires like these in multiple wire planes and do tomography, and that's how the far detectors work. You could also use a pixel plane and avoid potential ambiguities, which you need to be able to do in a high intensity environment, and that's how the near detector works. I'll say a little bit more about those specific technologies in a second, but this is the general idea of a liquid argon time projection chamber. So the far detectors, you can see here for scale how big they are. There's a little person below the one in the upper left. And so each one of these will have 17 kilotons, 17,000 tons of liquid argon. About 7 of that we're not going to really consider in our data analysis because it's close to the edge. We'll have backgrounds there, but 10 kilotons in the interior will be our so-called fiducial target. And so these are big detectors, as you can see here. We're going to start with 2 modules using 2 slightly different technologies, both based on this tomographic readout. One has a horizontal electric field, the other has a vertical one, and slightly different electronics and other technologies, but similar ideas. And then in phase 2 of DUNE, there will be a 3rd detector using the same vertical drift technology that we show here, and then the so-called module of opportunity, which means that if we can find the money and agree on what to build, we'll build something. But we don't know what it will be quite yet. So we're going to need a lot of argon for this, as you can see. And so getting the argon and keeping it there, lots of challenges involved with that, but I won't go into that. Instead, I'll talk now about the near detectors. So these are much smaller. You may or may not be a person for scale here, but you can see by the staircases, and yeah, there's a little person there actually, much, much smaller than the far detectors. but just as important, because without them, we have no idea what beam we're dealing with. So we use this suite of detectors to constrain the beam flux and other systematic uncertainties like neutrino interaction cross sections. But because there's so much going on so close to the beam, the wire readout technology is just going to give us too much ambiguity. So we have to use pixel readout. And this will be the first time that this sort of technology has ever been deployed in large scale. It used to be thought that you can't do pixels and live with argon, you'll boil your argon. But here at Berkeley Lab, the technology was developed to show that you can actually do it, and that's what we're building. In addition, there will be some other detectors. There will be a downstream so-called muon spectrometer, because muons like to travel in these nice straight lines and punch through, and so we need to catch them. And we'll also have a roller system that lets us move the near detector on and off axis, which further helps us understand the beam that we're dealing with. Okay, so that was a whirlwind tour of DUNE. It's under construction and moving along quite quickly, so it's exciting times. Now I'll talk about NERSC. So anyway, in terms of DUNE computing in general, there's lots going on. We've done lots of simulations since we haven't had much in the way of real data. But we have had prototypes. We've had photodetector prototypes at CERN. We've had near detector prototypes at Fermilab, as well as in Switzerland. And with those, we have to run productions on that prototype data. We have to manage our simulations as well as our real data from the prototypes. And then we have to provide users with the infrastructure to analyze the data and support them when they encounter issues. Of course, we're expanding, and so in the future, we'll have real full-size detector operations. And depending on how things shake out, we may find a place for streaming and online analysis workflows as well. Supernova would be an example of a potential use case there. And I'll say a bit more about that later. But for now, I'll just start with the ancient history of DUNE at NERSC. So what we ran about 5 years ago, Corey was used to produce these so-called McDonald's plots you see in the upper right, which tell you as a function of this delta CP mixing parameter, delta CP violation parameter, how well you can detect CP violation. And that's the so-called sensitivity of DUNE, and tells you for what range of possible values that nature throws at us can we actually see this phenomenon. So lots of simulations and fits were needed to produce these plots, and that was done all on Corey. You can see this plot down here. It shows the hours used over time. If you can zoom out, it's much more amusing because you see a flat line and then it suddenly shoots up, kind of like what we saw yesterday in the talk about black holes. But I didn't have the zoomed out version, so my apologies. There are also activities integrating with the HEP cloud system that I'll talk about that allows us to use grid computing technologies with an HPC center like NERSC. There are also some tests of inference as a service as part of this collaboration with Fermilab. That wasn't formally a DUNE NERSC collaboration, but a lot of overlap between Fermilab and DUNE people. There were some initial beyond the standard model simulation samples produced using this HEP cloud technology. And another thing that I'll talk a lot about is the development of a GPU accelerated simulation for the near detector. That was all done here. The near detector prototypes, all the simulation and processing for those was done more recently here at NERSC. And yeah, in recent years, we've been using a lot of hours, on the order of 50,000, and quite a bit of it has been on GPUs. So Perlmutter has been essential to our work. And so I'll talk a bit about some of the development we've done here with the help of Perlmutter. And so if we go back again another 5 years or so, we were in a situation where the near detector didn't really have a simulation, and you can't really propose a design if you don't have the simulations to say that this design will work. And what we found was that the high number of pixels in this type of detector made it hard to use existing detector simulation code. So instead, a small group here decided to build something from the ground up, at least when it comes to the detector and pixel side of the simulation, and then take that piece and combine it with existing technologies to build up a whole simulation workflow. So one of the custom pieces was this R&D sim detector simulation that was built for GPUs. I'll say a bit more about that in a second. We also custom developed a Python data processing framework called Flow, which is more CPU-y and NumPy, not quite as interesting. But by combining these with existing packages like JL4, Genie, and so on, we were able to get something up and running quite quickly, and it's continuing to serve us quite well. So all that initial development happened at NERSC, and combining all these pieces, we ended up going with Fireworks based on NERSC's recommendation, using a MongoDB instance hosted on Spin. That's been working well for us. But DUNE also has a centralized production and workflow system called Justin that we're transitioning to. And I'll talk a bit more about that as well. First though, this LRDSIM package. So there are a few things about it that are somewhat novel. At least at the time that this was written, these features were novel, maybe today not so much, but it's completely written in Python. So despite being written in Python, it's what we call a high performance package. So you might find that a bit of an oxymoron. And we're still dealing with Python performance issues. I'll talk about that when it comes to NESAP. But anyway, it's written in Python, does most of the heavy lifting on GPUs using a combination of microphysical and path models that will benchmark data. And it is written in idiomatic Python and uses Numba to just JIT compile Python functions into GPU kernels. And that works surprisingly well. We also use CuPy for those manipulations that the library already provides for us, and everything else we just use Numba for. So I won't go into detail about how it works, but you can see it splits into two paths, one for simulating charge and one for simulating light. And since these detectors are aimed at measuring both charge and light, it tells you how to split interactions that happen close in time. We simulate both of these parts of the detector. Anyway, so I'll go on now to the other parts of the software stack. Next up, we have some reconstruction code. This was not developed really by our group here at the lab. This was developed mainly by a group at SLAC, and that's since then expanded to multiple institutions. But this is a machine learning based reconstruction package based on Torch. Perlmutter was used for a lot of the training and testing, as well as running it. SLAC's S3DF system was used as well. Besides Spine, there's also a well-known reconstruction package, battle-tested, known as Pandora, that features lots of algorithms and is used by the FAR detector already. Among its algorithms are some machine learning algorithms that would benefit from the GPUs that we have access to here. And the key point about reconstruction from the near detector is that you've got a lot going on. You have multiple interactions, and you have to somehow associate a bit of charge here with either this interaction here or that one there, and it gets pretty tricky. And so you need advanced algorithms in order to do that. And of course, for that, you need correspondingly advanced hardware. So it's been great to have the resources that we get here at Perlmutter. Moving on now to data as opposed to simulation. We have a prototype of this liquid argon pixelated detector called the 2x2 because it's a grid of 2x2 modules. These are about a fifth the size of the modules that will go into the full-size NDLAR detector, and that will be a 7x5 grid. So this is just, you can think of it as a mini liquid argon near detector, but the same underlying technology. We deployed it last summer in Berkeley Lab's so-called NUMI neutrino beam, and we recorded the first ever neutrino interactions observed by a pixelated liquid argon time projection chamber. So you can see some event displays here. This is real data, and basically raw data, minimal processing has been applied because this pixelated readout technology gives us 3D images right from the get-go. You can also see upstream and downstream of the detector, the so-called Minerva range. This comes from a repurposed experiment that Berkeley Lab ran, and allows us to see what's going on with the muons that punch through the light. So we ran this last year, and NERSC worked great for all kinds of operational needs, for our prompt processing, for data quality monitoring, for offline production. That was all done at NERSC. And now we're gearing up for run 2. This year, we don't have a neutrino beam, so we're taking data with a bunch of radioactive sources to better understand our detector. And we actually ramped up the high voltage this morning, so that's why I got here late. But yeah, it's an exciting day. So going back now to simulation, I'm kind of jumping around here, but we've got an ongoing simulation production campaign for the near detector as opposed to the prototypes. And this is going to be an essential sample for studies that we need for getting through the next round of design reviews so that we can finally gear up our production, our physical production of the detectors. And so it's the same overall workflow, but we're simulating the full 7x5 detector and the corresponding beam. And so it's a bigger challenge. And NESAP has been enormously helpful in getting LRDSIM to handle this sort of scale. Okay, and just a few other services that we're really grateful to have benefit from at NERSC. So we use Spin, as I mentioned, to host the Mongo database that we use for fireworks. We also use it for interactive event displays like the one you see screenshotted here. We use Jupyter heavily for analysis. We use the web portal to make data quality plots and static dashboards available to our collaborators who might not have a NERSC account. Really easy, just put the files there and you're done. And we use data transfer nodes for moving our data to and from places like Berkeley Lab and University of Bern and CERN and so forth. Finally, the hackathons and NESAC, as I mentioned, have been enormously helpful. We've learned so much about profiling code for GPUs and optimizing our code, and it's paid off in results that you can see here. For example, these plots that Madan made showing before and after the memory consumption of LRNDSIM, and you can see here the improvement we got based on the changes that we made as part of the NESAC program. So it's been so helpful. I can't emphasize that enough. Okay, so that's the recent past and present. Now I'll talk about the future. So as I mentioned, we are transitioning toward integration with DUNE's centralized production system. And so to provide some context, what DUNE provides to its collaborators is a aggregated global pool of compute resources. It's a giant HD Condor cluster, essentially. So you submit your jobs, and these are usually simple, like one file, single processor jobs, to an HD Condor queue, and then it can send those to grid sites, it can send those to HPC centers, cloud providers, and so on. And the idea is that DUNE collaborators don't have to learn 40 different job submission systems to access machines at 40 different facilities. They can just learn one system. So that uses the Gladden WMS system that integrates with HD Condor. And then going a step further, there's something called HepCloud, which adds support for features at HPC centers that Gladden WMS doesn't really meet. So things like weighing how to charge allocations, that's something that HepCloud can do. And more complex sorts of jobs that involve multiple nodes, like MPI jobs, that's not really something Gladden's do as far as, at least that's not what they're built for. And so HepCloud fills that gap. And this is all presented to users in the form of a workflow system called Justin. And it's designed to support a global system of users and storage resources and compute resources, and so on. And so you submit your job to Justin, and it will match that job to a compute site based on factors that include how close the data is to a given site. And so that's another way of making sure that users don't have to worry about that sort of thing. Justin also automates tasks like code distribution to grid sites, initialization of the container that your job runs in, cataloging the output of your job, making sure that input files are available, recovering from failures, all that is insulated from the users. And finally, tying it back to NERSC, the integration between Justin and NERSC goes via this HepCloud technology that I just mentioned. So we've started running some of our workflows using this system, and we're in the process of transitioning the rest from Fireworks to Justin. We also have a centralized data management system based on Rusio, which is also used by, for example, LHC experiments. Rusio keeps track of where copies of files are, but doesn't keep track of metadata so much. That's the job of something that was custom developed for doing another Fermi Lab experiments called Metacat. And so we can ask Metacat, hey, I want files from this calibration run, and Metacat will tell us what the file names are. Then we can go to Rusio and ask Rusio, where can we find those files? And Rusio will tell us that. And then ideally, the users don't have to actually do this step-by-step process. Justin will take care of it for them, but that's how these services fit together. And so NERSC's role here is to be integrated into the Rusio system as a storage element. And so we can just add a rule to Rusio telling it, hey, this data set, we want to keep it on disk at NERSC for this long, and so on and so forth. Another area that we're taking advantage of NERSC is in continuous integration. So we're working on getting our GitHub Actions to work with runners hosted at NERSC. Pigface's been helping us with that. And so the way this is implemented is with an API server that runs on Spin. When a GitHub workflow is triggered by like a pull request, then that workflow will use a webhook to call out to that API server. And then the server will submit a Slurm job that will then, within the job, call a single shot runner that runs the workflow after verifying that it's an authorized user who actually triggered it. And so our main motivation for this is to be able to run integration tests on LRNDSIM so that we can start doing bigger refactorings and not have to manually run a bunch of tests ourselves every time. We can let continuous integration take care of that for us like it should. Now, completely changing tacks. 1 more minute, okay. I'll wrap this up. So, yeah, if we got a supernova, that would be awesome. The thing about neutrinos is they come long before the light from a supernova. So we could not only learn a lot about core exploding star by recording the neutrinos, but we could also tell telescopes, optical telescopes, where to point. And so the data volume here is a major challenge. And it's still an open question of exactly how we want to implement such a solution. But we do hope that NERSC can be a part of that solution. We've been working on taking the lessons we've learned at NERSC and applying them to other sites like ALCF, OLCF, and all of the work that DUNE is going toward standardizing its software stack will help with that. We also need to be thinking about porting to other GPU architectures. Hopefully the ARM transition will be pretty simple since most of our code should just work, but GPU architecture is another story. SPAC will help with packaging our software in a standard way, and NERSC also provides SPAC facilities, so hopefully there will be some good alignment there. The release of SPAC 1.0 is a welcome development. We have a next generation framework that we are hoping to test at NERSC, specifically its accelerator integration features. And with that, I will wrap up and just say that DUNE as an experiment is really grateful to NERSC and the DOE for all the resources we've been able to benefit from, not just computing resources, but people. All the help we've gotten from them have been absolutely invaluable. That includes NESAP, the hackathons, training events, support via ServiceNow, all of that. It's had major impacts on DUNE science program. We're publishing papers based on the work we do here. And we're really excited to continue this collaboration, especially as DUNE comes online. So thank you.
Yeah, go ahead.
You said supernovas, where you could detect neutrinos, are once in a lifetime event. But like reality, like what is, like how many detectable supernovas where you can detect neutrinos happen? Like what's the frequency at which that happens, in which we can detect it?
I think the number that gets thrown around is like 1 or 2 a century, something like that. Something that would produce enough that we can get meaningful science out of the neutrinos. But it also depends on like how big your detectors are, because as you get to bigger detectors, then you can see farther off neutrinos, or farther off supernovas. So it's a bit of a wishy-washy answer for me to say once a century, but roughly on that order.
1987 was the last one.
Yeah.
50 years ago.
We got like a dozen neutrinos out of that one.
Okay, there's a question online. Okay, you had many different flowcharts and representations of workflow interactions in your presentation. Is there something that you use to generate all of these different workflow presentations? Like, do you have, are people just making their workflows, or?
People are just drawing these,
Okay.
but
How do you keep track of all
the
that?
nice thing about using fireworks is that we can define our workflow as a graph like this, with
Okay.
steps, with dependencies between them and multiple branches and so on. So the workflow we define in our Python code looks just like these flowcharts. And that's been one of the things we really like about using this.
Okay.
And that's also something that Justin will provide.
So Justin can make workflow charts for you,
Well,
like representations, or just make the workflow?
Just make workflows.
Okay.
And right now, I think it's mostly linear workflows that Justin does. So adding these branches or things split off and join back together, I think is a feature that's still in the development stage, but it's planned for the near future.
Yeah.
You mentioned Justin using HEP cloud as a future work. How much has accomplished? What is your target date?
So the target date is about 6 months ago, and it's actually worked in the past. I think most of the challenges have been just small technical things, like the fact that we depend on HT Condor libraries, and the container that Justin has switched to with the Alma 9 transition doesn't include those libraries. So it's little things like that, and just the fact that everybody is doing so many different things that it's just kind of been sitting on the back burner for a while and moving slowly, but it is moving along, and hopefully within, say, a month or so, we'll start running more tests. We were already able to run, some recent campaigns, and then the Alma 9 transition kind of slowed our momentum a little bit, but we hope to pick that back up.
People don't have to worry about batch scheduler, the differences at different sites. What about executables? Do they have to, like, when you prepare this type of workflow, do they actually have to, in the background, somehow it's built in 4 different machines
So
already?
what we're aiming for is to standardize on an Alma 9 container. So unless you have a really fancy stack that won't work with that, the idea is you build for that standard container, and then that's available on all sites you run on. With GPU code, it gets a little tricky because we might need to use different CUDA library versions on different hosts, but we hope that using a feature like app containers -b, we can just map those in. Hopefully things will just work and we don't have to rebuild anything.
Thanks, Matt. Okay, we're gonna get the next presenters set up. Okay, can I get your laptop here?
Oh, good. Good news.
Nice, perfect, right? And then try,
Oh, yeah, perfect.
excellent. You do like a one.
Okay, hi everyone, I'm Burak. I'm a fifth year PhD student of Professor Mohammed Kandemir from Penn State Computer Science and Engineering Department. Today I'll be presenting my ongoing research that I started at Argonne National Laboratory this summer with Dr. Krishna and Ishwan. So first, an introduction to the research problem. Ocean dynamics simulation is simulating the movement, temperature, salinity of ocean water across dozens of years, across long time periods in the future. However, fully simulating this is very expensive. There are methods to speed this up, such as using a coarser grid size in simulation. But this results in a loss of information in subgrid things like eddies and vortices smaller than a single grid. And this would lead to errors in simulation. To deal with this, we use subgrid parameterizations to define the net effects of these missing eddies and vortices on the simulation. However, determining these subgrid parameters is very difficult. They're usually tuned and calibrated against observations and different data sets and resolutions and regions. And this isn't cheap again, because you need to run a simulation, see how well it performs, and again, it takes some time to do. So the goal of this research is to make a machine learning surrogate model of a physical simulation to accurately forecast ocean dynamics with regards to these parameters, which would make choosing the ideal parameters for simulation much simpler and cheaper. Or even if this can be used as a replacement for the simulation, if sufficient accuracy is achieved. In order to make a machine learning model, the most critical part is obtaining enough high quality data. Real data from the ocean is sparse and across short time periods, making it difficult to use a machine learning training. So instead, we use a simulator called MPass Ocean to simulate in a data set called SOMA, which is an ocean basin, a bowl-shaped kind of region, 150 kilometers in diameter and a grid size of roughly 1 kilometer squared. And we ran 100 different simulations with different subgrid parameters. And each simulation was run for 23 years with a 2-week time step. And this was all ran on Perlmutter NERSC system, and this resulted in roughly 700 gigabytes of training. So this training data consists of 5 parameters, and some of these are visualized on the right side. So these are the zonal and meridional velocities on the top, which is the flow from east to west and north to south. We have the temperature, salinity, and layer thickness. In addition, I also have different parameter configurations for each simulation. So right now, this project is still in a design space exploration stage. So there are many ways of making a machine learning model. And I'm trying different combinations, seeing which one performs well for our data set. So there's roughly 3 design choices that I'm going through. The first is the inference framework, which is essentially how will this machine learning model be used during inference? Second is what kind of machine learning architecture to use. And the last part is how to compute the loss during the training, which is measuring the error between the prediction and the ground truth. This loss is used to update the model parameters using some algorithm like gradient descent. So this problem, a popular way to solve it is a method called graduate student descent. Finding a graduate student with this problem. And they try things until they come up with a solution. So the next 3 slides, I'll go over these in detail. So the first is the inference framework. And what I'm using is some model from a state-of-the-art paper called spherical diffusion. And I chose this because in the paper and empirically, they showed to be much more stable than other forecasting methods. And by stability, what I mean is, for example, if you train a machine learning model to predict 1 year in the future, if you want to predict 100 years, you would use this autoregressively, which is you predict 1 year, take the output, use it as the next input to predict the second year and so on. However, this leads to an accumulation of errors. And usually what happens is if you do this for long enough time, you get impossible conditions such as the ocean boiling or things like that. So this method, spherical diffusion, was shown to be stable over a long period of time, which is why I chose it. And this method consists of training 2 separate models. So one is the interpolation, which is given 2 frames as input, you try to predict an in-between frame. And the second model is the forecasting model, which given 1 frame as input, you try to predict a frame in the future. And interpolation is much more easier to learn than forecasting. And what this model does is, as shown in this animation. First, we have some data, X1. We make a forecast using the forecaster architecture, predict X4. And using X1, X4, we interpolate X2. Then we use X2 to refine the forecast with the forecasting model again. We do another interpolation, get X3, and so on. We refine the forecast. And if you're familiar with diffusion-based machine learning models, this is based on that. It's very similar. And this has a few additional benefits as well, such as it can predict a distribution of states in the future. And it can predict in finer timescales than what was used in the training data. Okay, so initially what I tried was use a state-of-the-art model, see how well it performs on my data. And the state-of-the-art model in the paper was used for worldwide ocean climate prediction and with very good results. But for my data set, it turns out it didn't work as well. And the reason why it didn't work well is because the data that I'm using is much smaller in resolution. So I have a 1 kilometer scale, 1 kilometer squared data resolution, whereas in the paper, it was 100 kilometers squared grid size. And this results in observing much more chaotic details, which are difficult for the machine learning model to learn. And this should show an example of this. So on the top side, we have the real frames. And on the bottom side, I have the predictions from the machine learning model. And the brighter colors in red are fast-moving flows, and the purple ones are slower-moving. So the fast-moving regions are predicted well. They're almost identical in the prediction and the real frames. However, the purple regions, the slow-moving regions, where you can see eddies, the swirls in the images, they're not predicted well. In the real data, you can see that these eddies actually move around the data. Whereas in the prediction, the machine learning model can't predict these correctly, so they're static or they get distorted easily. And the reason why these slow-moving regions aren't predicted well is due to the loss function. For example, mean squared error. It's not giving a large enough penalty to slow-moving regions, which results in the model not learning these well. It doesn't prioritize the slow-moving regions compared to the fast. So to fix these issues, I did 2 things. So one is I modified the loss function to include additional components. which were derived from the data, such as including the flow direction angle, the vorticity, and other similar methods. This results in the machine learning model penalizing these slow-moving regions, these eddies, more and learning them better. And it also results in faster training. And the second thing that I did is adding components to loss function based on physical constraints, such as the conservation of flow, the kinetic energy formulas, and similar. And this results in better prediction as the machine learning model starts to learn these physical laws and follow them. And this is referred to as physics-informed machine learning in literature. And the final loss function looks something like this on the bottom. So we have the original mean squared error loss, we have the data-derived portions that I add, and the physics-informed parts. And all of these have to be balanced. So if you weight one component too much or too little, that can result in degraded performance. So choosing these hyperparameters, alpha, beta, and gamma, are also critical to model performance. And the last design choice is the machine learning architecture. So the baseline architecture that I'm using is a model called AI2 Climate Emulator, which is one of the best models that's open source for ocean prediction and climate prediction. And the most important component of this model is something called the neural operator block, or the Fourier neural operator block, as shown in this image on the top. So the idea behind this is you convert the input data into Fourier space, and you learn parameters in Fourier space and convert it back to the original space again. So just like in math, where some problems are easier to solve in Fourier space, it's the same thing for machine learning. And this Fourier neural operator has been used in several climate and ocean models with very good results. And the entire model is something like this. It's a simplified view. We have an encoder which converts the input grids data into a higher dimensional space. Then we have a series of these Fourier neural operators. And finally, we get the output and decode it back to the grid space and obtain the forecast. So the main design choice that I'm exploring here is what kind of neural operators use. So different neural operators work well for different problems and different kinds of data. So for example, standard Fourier works well for two-dimensional or three-dimensional data where the grid is uniform. There's also a spherical Fourier transform, which works well on data that's located on a sphere, such as the worldwide ocean data. And there's other kinds of operators as well that convert into different spaces, and there's ensemble of operators you can use. And these are all things that I'm exploring right now. And the final slide. So like I mentioned, this research is still in progress, and I'm at the design space exploration stage. And what I'm doing right now is trying different methods and evaluating it on my data, seeing how well it trains, using some graphs like validation and loss curves. And how I'm using NERSC right now is I'm training models, and roughly a full training takes 16 nodes with 4 GPUs. So roughly 150 node hours, which is around the 600 GPU hours for full training. And again, there's roughly 700 gigabytes of data that I need to actually load to the GPU. So I have high data IO, plus I do periodic checkpointing. And what NERSC enabled me to do is go through this design space pretty quickly and find what works and what doesn't work. And for the future work, what I'm planning on doing is testing the best performing configuration on a larger set of simulation parameters that I want to analyze from MPAS Ocean, running this on different data sets to see if it generalizes to different conditions. And finally, testing some other novel architectures, such as there's physics-informed machine learning models, which has the physical constraints actually baked into the model itself. There's also ideas of incorporating attention mechanisms, which is the backbone of LLMs and VLMs, into this predictor and see how well it performs. And that is all for my presentation. Any questions?
You said simply you predict data into Fourier space, but I'm wondering, like, is there like an arbitrary latent space that actually would be better for your model? Like, right, it seems like not necessarily arbitrary, but like, could you make something that's arbitrary and optimal with an autoencoder or something? That makes sense. Or maybe this is a stupid question.
You might.
It might be a stupid
I
question.
mean, I need to try that to see if it works or not, but it's completely possible. You might actually learn this space to transform with parameters. So that's actually an interesting idea to try. Any other questions? Okay, thank you all for listening.
Yeah. Thank you.
Just make sure to stop sharing. You know, I need to start sharing.
Yes.
All right, cross my fingers. So the video's good. All right. Should I start?
Thanks.
Everybody, my name is Will Liberti. I'm really excited to be here. I'm a neuroscientist and engineer. And also, I am part of the, I think, 1% of NERSC allocation that goes to small business. So I'm actually part of the Lab Embedded Entrepreneurship Program. It's called Cyclotron Road. This is actually an image of Cyclotron Road from the 50s. And NERSC would go up here. And so NERSC hasn't been built yet. And I'm going to talk today a little bit about physical or embodied AI. Everybody, when you ask like my parents or friends about AI, they usually think about the sort of superhuman capabilities of large language models, like ChatGPT. They can perform, these crazy tasks. They can be better than physicians at reading radiology diagnostics. They can, synthesize huge amounts of data that we just really can't do. And so I want to talk a little bit about like how this is translated into the physical world. So I'm going to talk about robots. So this is a video. I don't know if you guys are aware, but the first robot Olympics just took place in Beijing. And this is 3-on-3 robots. And they're doing actually a pretty good job. They mostly are standing upright. Oh, was losing his balance. So again, So compared to the superhuman abilities that these large language models have, then he scores a goal. And then he just gets in trouble. So compared to the superhuman abilities of these large language models, this hasn't really quite made it to the world of like robots, right? So this is like the science fiction dream. It's sort of like not in alignment with maybe what we would have expected like 20 years ago. And this actually hasn't been lost upon roboticists or our neuroscientists. So this concept, a general idea is called Moravec's paradox. Whereas if you take perceived computational difficulty as a function of evolutionary development, like we are very at the end apex of evolution on this planet, we can reason and we can speak and we can do really complicated things compared to something early in evolutionary history like microbes. For AI systems, for whatever reason, seem to be really good at doing the things that are really complicated, but they seem to not do such a great job at things that we think of as very simple, like to simulate what an ant or a spider could do is like very, very difficult to do. But to simulate like one of the best, we can solve these mathematics problems. They're very, very difficult for people to solve. And AI seems to be able to handle that very, very well. And so this is very strange because you have, like I showed this video of robots, like walking around trying to kick a ball, but things that are so effortless to us, like buttoning up a shirt or like zippering something or folding laundry where some of the laundry is inside out. or tying a shoelace, like something a 3-year-old can do. These are like huge unsolved problems in robotics. Like we are not anywhere close to doing this. And it's not a hardware problem because if a person can actually teleoperate a robot and actually learn to do this pretty well, but it's very, very hard to figure out how to make an autonomous system do this. And so I think that there's a reason for this, so it will be familiar to everyone here. If you take all of the examples of superhuman abilities of artificial systems that have either reached human level parity or superhuman ability, either in chess or image recognition or self-driving cars. We didn't figure out something super clever or heuristics about how humans tend to do this. We just get a ton of data, and then we use very basic, simple, statistics to figure out, what is it about like transitions of sequences in this data that get us these sort of phenomena. So this is a concept from a very popular science article from Richard Sutton. This idea is called it was called the bitter lesson. Sutton and Bardo, if anyone took reinforcement learning in the last 20 years, you probably used their textbook. And his conjecture was all progress in AI basically come from compute with general statistical methods and a ton of data. And so for large language models are trained, there's a huge amount of training that goes into them, but also they have a huge corpus of data. They have a whole internet of tons and tons and tons and tons of text. And we just don't really have something like that for movement. So if you were to say like, and this is a problem because things that are difficult to explain in words, like telling someone how to do brain surgery, or telling someone how to tie a shoelace, like if it's hard to explain how to do this, it's not really embedded well in these spaces. So if we were to have like a back of the envelope calculation of like, okay, well, how much data would we actually need to make a system, an artificial system that would perform sort of like at the level of language models? So you take like a GP2 level model. So let's say, because we know how big their data corpus is, imagine like 1.3 tokens per word. Imagine that like instead of like you're signing it, right? So let's say we're trying to capture dexterity of human hands. Like it takes, for American Sign Language, we can sign about 120 words per minute. So to reach like a GPT-2 level corpus, it would take about 900,000 hours of continuously signing. Now, if you were trying to train like a more frontier model, like Llama 3, this is released from Meta last year, it'd be about 1.6 billion hours of signing. This is just like a crazy amount of data. We don't even know how to capture this kind of data, right? So, how do we do this? This is what I'm trying to do. So we're taking a very strange approach where we're building neuromuscular interfaces. These are systems that you could wear on your wrist that capture signals that are going from your brain to move the muscles of your hand. So in those signals are projected all of the movements and forces that your hands produce. And so we're taking this data and we're aligning it to measurements of ground truth. So this would be things like cameras and force sensors in a very, very controlled environment. We're throwing all this into a deep convolutional neural networks with some tricks. And we get out, we try to predict hand pose directly from raw neuromuscular signals. So what practically speaking, that looks like, we have a lab, it's actually in building 62, not far from here. If you want to see it, I'm running a study, you could use your data. So what you would do is you would stand in a room like this is me, and it would move around. And then there would be cameras in the corners. And these are, it's a computer vision model that's tracking where my hands are in space. I'm wearing neural interfaces on my wrist. I'm trying to build these very, very large models with lots of people so that I could just put my device on the person, pick up those signals, and then guess pretty accurately what your hands were doing. So I'm going to show some output of what this looks like. So this is Kevin, one of the members of my team. He's going to kind of walk in, put a device on his hand. He's going to pull up a specific model just for him. So Kevin. And he's going to move his hands around. This is live decoding from his neuromuscular signals. And then for fun, he's going to fly a drone around. That's basically conditioned on specific gestures that this dude.
Everybody's really impressed with the drone. Like Department of Defense is like, how do you do that? How do you fly the drone? It's like, that part was really easy. The hand part was really hard. And more than that, so we're not just tracking like positions. You can sort of do this with the camera. But we're also tracking fine forces. So here's what's actually kind of complicated. This is Kevin again. He has a device on his wrist. He's going to pick up some tweezers and pick up two objects, sort of squeeze. This is actually a good video to watch this one. And then this reconstruction of his hand from the signals. And below I'm going to plot force, like how much force he's applying to this. So his hand actually is not going to move that much. The pose doesn't change very much. But you can see he gives it a little squeeze. There's a lot of information that's not just in the position of the hands, it's in the force. He picks up a nut, which is heavy, so it's a lot of force. Picks up some foam, gives it a little squeeze. So these are all things you can decode with these kinds of devices. That's it. So having access, I know everybody people have been saying this before, but for us, like having access to NERSC has been like actually really, really, really huge deal. As like a small business, like we're super, super under-resourced. And like to do the kinds of things that we're doing here, just like would not be possible. And it's not just access to the resources. Like for us, we're a team of 4 people. None of us have ever run any kind of simulation that goes beyond the capability of this laptop. But just like being part of a community where it's okay to learn mistakes has been really, really huge. And I'm really, really happy to be here and thank you for giving me the opportunity to speak. And if anybody wants to come and see the robots or hang out and get your data taken, I'd be very happy. And you'd be doing us a huge favor. So please find me after. Happy to take any questions about this work now. Any questions?
Is the complexity of having of how the movements work at all similar to how people figure out how to make prostheses work?
Yeah.
With the okay.
And so if you look at, so this is what I used to, so I'm a neuroscientist, actually mostly worked in invasive implants for neuroprosthetics. And there it's very difficult, it's very high dimensional, like your hands can move in many, many dimensions. And so what tends to happen is you try to record something reliably with very low dimensions, like something like open and close, like your hand. It ends up being that many people, they just want something that's super reliable, it's going to work. They don't necessarily want to get all of the articulation back. They just like, I want to be able to not randomly do something that I didn't intend to do. But yeah, so this kind of stuff, like if you had better models of how you tend to move, maybe you can move more intelligently with like lower dimensions. You can actually decode well. Yeah.
So the sensor that was placed on Kevin, what is all of the movement that he was doing really being read from that one sensor?
Yeah.
So like even
Well, it's like an array of sensors.
it goes all the way around. Like
Yeah.
even just translating your arm in space, it's able to do that
Yes.
just from this.
Yeah, so it's actually like so like I can cheat and put like an accelerometer on there and then do that. But here I didn't cheat. These are all real videos. Like you have like different like blood flow changes and like just different musculature changes as a function of your posture. So like you can use that. And then you have some priors on like, okay, your hand's probably not going to float away. So there's some like
boundaries.
there's some boundary conditions you can set so that makes the decoding problem a lot easier.
So you mentioned that this is easy for humans, difficult for robots.
Yeah.
But essentially both use some kind of reinforcement learning. Your babies can't move around, but try and fail and learn the movements. And what makes humans different from the method, from kind of software-based reinforcement?
Yeah, so this is like
What's
part.
special about?
Yeah, so this is a great question. So again, like as a neuroscientist, like I failed making systems that can behave cognitively, and the computer scientists have won. And the way that they've won is they just like sample tons of data. Like self-driving cars is the same thing. Like it probably took me 20 hours, 30 hours of practice before I could drive a car really well. But like, you know, we're on the almost million hours for self-driving cars to be able to perform just at like regular human capability. So some of it's priors. Some of it could be like a deer is born knowing how to run. So there's all this like genetic predisposition on like, you know, there might be stuff that, you know,
You can't train like a macaque, a rhesus macaque, or a primate to speak. You never will. They have the machinery to do it, but they don't have the cognitive capacity. There could be something to genetics that predisposes you to be able to do this that we just don't understand. And so part of the bitter lesson is like, well, it just tends to be if you just sample the output statistics of this, you can kind of make generative models that work better than whatever it is that people are doing. That makes sense. So yes, there is something that we're doing that's way more complicated, it's way more interesting, that uses reinforcement learning. But in practice, just having a system that you can sample the statistics from just gives you better results, which is sad. And that's why bitter lesson for Richard Sutton, because his textbook is all about reinforcement learning. And it's like, actually, it turns out, maybe you don't really need as much for deployment.
Is Spindrift branching into making robots?
We, this is a picture from the lab, and we put this online, and I sent Spindrift a note and said, hey, we have this picture that kind of looks like we're advertising Spindrift. It's on the National Lab website, just so you know we love your product. And they sent us a coupon that we could use at Costco. So for basically a limited Spindrift, this says free Spindrift, so we can bring it every time we go. So I feel like it's appropriate to put Spindrift on here because they're kind of sponsoring, we drink a lot of Spindrift. Thousands of dollars of Spindrift that they consume, which you too can consume if you come to those.
That's really cool.
Yeah, so.
I thought maybe they were developing a robot to help them with
I would
drinking
love
more
to.
Spindrift or
I would
something.
love to. My communication thing was very smart. So I was just we love your product, and then just oh, here's a coupon.
Nice.
Who else can I message? Does Hot Pockets also have that?
Awesome. Thank you so much.
Yeah, thank you so much.
Okay. Our next speaker is Vijay, who I think you're muted still.
Hello, good morning, everyone.
Good morning. Okay, go ahead and share your screen. Vijay was hoping to be here in person, but funding didn't work out, so we're still including this presentation. And
Hello, can you hear me?
yes. Okay, perfect. Thanks so much.
Okay. Hi, good morning, everyone. So this is Vijayalakshmi Saravanan. I'm an assistant professor at the University of Texas, Tyler. At Tyler. So I'm going to present today's talk about my DOE funded ASCOR FAIR funding project, which is titled An Efficient Storage Driven Machine Learning Model for Performance in the Era of Multimodal Scientific Data. So I'm the principal investigator for this project, and then co-investigator is at Albiona Lawrence Berkeley National Lab, Dr. Khalid C. Ibrahim. So today I'm going to talk about the containerization at the NERSC Perlmutter. So what are the challenges we faced when we started with our project with respect to the NERSC containers as well as the HPC scientific workflows? And outline of my today's talk is I'm going to give small introduction about our overview of my research as well as the performance optimization. Then what are the challenges we faced using Docker, then why we moved from Docker to the Singularity containers, and then sample scientific use case, which I'm going to present in this one. So the overview of my research is about, so we are currently dealing with the massive amount of data as well as the massive resource utilization as well. So that's the reason we need to, come up with a solution called how effectively we can store the data as well as the multimodal in nature as well. So that's when this proposal came up into this picture, and then we were currently working on the massive amount of data which is simulated from the different national lab facilities like Brookhaven National Lab as well as the Lawrence Berkeley National Lab. So the data and the processing demands which requires a lot for, especially with respect to our high performance computing scientific workflows. So massive data volumes are generated as well as simulated from the different sensors and then scientific simulator and then oscillators. And this data could be both, I would say like a data intensive as well as the computationally intensive. And then we also dealing with multiple heterogeneous hardwares like a CPUs, GPUs, as well as the FPGAs. So which is always giving the problem of the complicating the dependency issues while we are deploying in the HPC ecosystems and all. So at the same time, we need to utilize the resources, optimize the resources properly so that we will be able to optimize some resources as well as save some storage space at the end. So that's the whole idea of my proposed work, wherein we are proposing the multi-tier storage driven solution with respect to the multi-modal integration of the data with respect to the scientific different kinds of the scientific data. So next question is like, why do we need the containers, right? So as I mentioned, our workflow consists of the real-time streaming of scientific data, which is if you go with the containers and all, so we will be able to process the data effectively, and then we will be able to deploy the cross systems. Like we wanted to deploy not only the NERSC Perlmutter at LBNL, we wanted to utilize all the scientific workflows from the BNL, Brookhaven National Lab, as well as the ORNL. So the cross-system portability is very quick with respect to the containers, and then real-time streaming of scientific data, which is also improvise our data processing, and then we will be able to quickly get the insights as well, right? And then the containers also we utilized for optimizing the IO bottlenecks, and then we wanted to streamline the data management. So basically the efficient usage of the storage, that's why our main concern about the overall project. So when we started this project, we had multiple, issues or the challenges we faced. We started with our HPC clusters in Brookhaven National Lab. So due to the old, systems of the Linux environment, so we are unable to process the, high performance computing data as well as the high size of the data. So that's the reason we moved on to the Docker. So when we supported with this NERSC Perlmutter, so that's when also now also we are just limited support with the container, I would say, like a NERSC Perlmutter. So we are using the container in the a NERSC Perlmutter environment. So the previous process, poses the unique challenges with the traditional workflow environment with the HPC clusters at Brookhaven National Lab. So that's when we moved to the Docker at NERSC Perlmutter. But now also we are facing some issues with the, especially the security issues, right? So the Docker, which has the root privilege access, privilege access, denial of this one. And that's the reason we wanted to explore more about the singularity container. So that is going to be avoided through the root access issues, as well as which is also giving the greater security with respect to the different HPC applications, as well as the scalability and efficiency, which is also giving the better performance and then scalability with respect to the HPC workloads compared with the Docker. So for the use cases, as I mentioned, we just take one use case from the Brookhaven National Lab, which is, the data set, the data is derived from the NWChem, molecular dynamic trajectory of data. So we utilize the scientific simulation and then data handling from the NWChem, which is the high performance, computational chemistry software, which is producing the PB and TB of data. So we collected all the molecular dynamic data trajectory, and then we proposed the solution called the multi-containerized in situ sampling framework, which is going to evaluate the existing online sampling algorithm for the improved efficiency as well as the scalability. So the goal for this approach is like containers, which is we package all the change point detection or the any kind of a machine learning algorithm or the analytics part in one container, which is going to enable the producer and consumer architecture with the multiple container nodes. At the same time, the data flow and then processing of the multi-molecular data, which is producing multiple data. So basically the NWChem data, which is going to simulate and collect the molecular dynamic data trajectories, which is going to be packed in one container. And then while the other OAS container, that is the online adaptive sampling container, which consumes the data and then which is going to process it and then which is going to give us the if there is any anomalies or there or if there is any change point occur or not in the real-time streaming environment. So that's the whole idea for this containerized approach. And then when we integrate with the EDIOS adaptable IO system for the seamless as well as the efficient data exchange between the molecular data container as well as the OS containers. So this is our sample framework. This molecular data, which is similar, collecting the data from the NWChem data, molecular dynamic data trajectories. Then we incorporated with the EDIOS 2. And then this is our online sampling algorithm. It could be any kind of a machine learning analytics or the algorithms. It could be a statistical approach or the, any kind of a machine learning approach. So we were utilized this, single container approach only right now. So we plan to deploy the system with multiple containers so that the NWChem data, the producer is going to produce the multiple large amount of data, then containers which is going to be utilized for one containers for the online adaptive sampling, and then another container is going to act as the dimensionality reduction as well as the any kind of machine learning analytics we can perform so that it could be a kind of a microservice containers. So right now it is in a very early stage. We just deployed with the container only. We tested out without the container and the HPC environment for the singularity, but we are still struggling with the singularity container in NERSC Perlmutter. So the preliminary results shows that when we containerize our multiple, producer and consumer concept with respect to the NWChem molecular dynamic trajectory, we achieve the reduction of computing time as well as improved resource efficiency. We published this paper in last month in Europark conference, virtualized high performance computing workshop. And we containerize the synthetic data with the GPU accelerator, which is also predicting very faster compared with the traditional system, as well as it is also reducing the infrastructure cost. So the best practice so far, as I mentioned, this is still in immature state, preliminary state, because when we started this project, after that I moved out from one institution to another institution. So uh, almost like 1 year, we never. That funding got transferred. Now only we are into full swing. We are working on this project. So when we implemented this in NERSC Perlmutter, so we were come up with some best practices and recommendations. So if you could go with the performance optimization is your main target, everybody's target is performance, right? So we can optimize the resource allocation with assigning the specific CPUs to the containers. So that is going to improvise the performance. Still, we are working on this part now, as well as the GPU virtualization, because of the across the multiple containers, it is going to degrade the performance, but we would like to increase the performance with respect to the GPU virtualization. And then security, the best practice is like you can use the minimal images, base images with the minimal privileges to the users, so that it is going to reduce the risks of the security risk. And then we can also do the vulnerability scanning, and then you can also monitor the logging and then performance resource usage in real time. So we are planning to implement the auditing mechanism for the security compliance and the data tracking. So yes, the future works, as I mentioned, like, we wanted to optimize the singularity for the diverse high performance scientific applications, because right now we have the access with one data set. We have tested out with that NWKM data. Currently we are working on the OCP data, Open Catalyst project data. So, and then we are planning to expand our additional simulation for and ML machine learning framework to enhance our HPC utilities. So right now, we are successfully achieved the OES with a single container, approach with the producer consumer architecture concept, and then we are planning to deploy in future with the multiple container, perspective of additional simulation as well as the additional machine learning frameworks to enhance the HPC utility. Thank you. Any questions?
Any questions in the room? Okay. We don't have any questions online either at this moment, so if you think of anything, please reach out to Vijay. Thank you so much for your presentation.
Thank you so much. Thanks, Libby.
Use your one.
Yeah.
Okay, sounds good. You can. So you're in, so now you can.
Oh,
share.
sorry.
Yeah,
I forgot.
Okay, all right. Well, finally, the moment has arrived from yesterday. And Khanak is going to be our grand finale speaker. So
I'll try to be quick.
no. You don't have to do that. We're good. Okay, thanks so much for being here, and yeah, take it away.
Of course. Hi, everyone. I'm Khanak, and I'm a physics PhD student at Stony Brook University in New York. I work with Professor Michael Zingale, and we basically blow up stars on supercomputers, or at least he does, and I'm still learning how to. So the main focus of my research is to understand the progenitor systems of type 1a supernovae, which are very bright thermonuclear explosions of white dwarf stars that are found in binary systems with a companion star. For people who are in observational astronomy, spectroscopically, they do not have any hydrogen emission lines, but they have a characteristic silicon-2 absorption line, which is how we distinguish them from other types of supernovae. Why do we care about them? Well, in nuclear astrophysics, they are important because they enrich the interstellar medium with heavy iron group elements, which is why we exist. More than half of the observed iron in the universe is basically because of these explosions. Then in cosmology, they're used as standardized candles or as distance indicators, which is how we discovered dark energy, or the fact that the universe is constantly expanding. And yet very little is known about their origin, and a lot of questions remain unanswered. Questions including, but not limited to, what is the structure and the composition of the white dwarf that explodes into a supernova? What is the nature of its stellar companion? What is the detonation mechanism through which it explodes? And then what is the effect of the initial conditions, such as mass, composition, the ignition, on the observables and the yields? And so in an attempt to answer all these questions over the years, two main formation channels have been envisioned to give rise to these explosions. The first is the single degenerate channel, in which basically we have a white dwarf star that accretes matter from either a red giant or a main sequence star, and it basically explodes as it reaches the Chandrasekhar mass limit of 1.4 solar mass. And then the other one is the double degenerate channel, which, as the name suggests, has two white dwarfs that dynamically merge together, leading to a type 1a explosion. I am particularly interested in a special case of the double degenerate channel, in which the primary white dwarf explodes via the double detonation mechanism. So this can happen in the case where we basically have two carbon-oxygen white dwarfs that have thin helium shells around them. And so this primary white dwarf, which is the more massive one, because white dwarfs, they have an inverse mass and radius relationship. So the more massive one, it accretes helium from the secondary star. And this can lead to a surface detonation on the surface of the primary. And so this first detonation on the surface, it sends shock waves into the core of the primary. And if these converge at a point or anywhere in the core, basically, that can trigger a second or the carbon detonation that can explode the entire star, and that event would look like a type 1A. So in my case, the key questions, they come down to exactly what conditions trigger the first surface detonation, under what conditions would the second or the carbon detonation possibly take place and lead to a type 1A event? And if that does happen, then what happens to the secondary star? And in this case, that's another white dwarf. So far, there's only 2 other groups that have done full 3D simulations, and both of them have conflicting results. One says the secondary detonation does take place, the other says it does not. And so I'm hoping to be a tiebreaker. I would like to be. And so we are tackling this problem by using AMRX code called Castro, which is written in C++. It solves the multi-component compressible hydrodynamic equations. It also has the capability for self-gravity, nuclear reactions, as well as radiation. It uses an Eulerian grid with adaptive mesh refinement to help with computational costs. For hydrodynamics, it uses the unsplit version of piecewise parabolic method. And for coupling of hydrodynamics with reactions, it offers the traditional strand splitting method, as well as 2 types of spectral deferred corrections. We can now run Castro fully on GPUs, so that's good for us. I want to highlight the last 2 points over here because that's what sets us apart from other groups and the codes that they use. So over the last few years, our group has been focusing on strong coupling of hydrodynamics and reactions because this has always been very challenging in such astrophysical simulations. In traditional operator splitting methods such as strand splitting, reactions and hydrodynamics, they are treated separately in a staggered manner. Now, of course, this makes our integration easier, but this does not do well when temperatures are really high. And what happens is when in stars, in regions, when temperatures are super high, nuclear energy is released faster than hydrodynamics can respond. And so that basically leads to breaking of this coupling, and hence we lose numerical accuracy. On the other hand, in our case, we basically use a simplified version of spectral deferred corrections in which we basically explicitly couple both hydrodynamics and reactions together at the same time. And so this basically helps us maintain that accuracy and also, of course, the coupling. Last year, in fact, our group did a study in which they specifically tested this method for the case of double detonations, which is what I'm trying to do. And we found out that not only does it maintain the accuracy, it is also more efficient when we have a lot of burning, which is what happens in detonations. So we thought that the best way to approach this problem in my case would be to just pick up the initial conditions from one of the other groups and try to recreate it using our code and see how it does. And so this, moving forward, I'm like, when we get to the fun part, when we talk about the simulations, just bear in mind that this is like one of the preliminary runs. I still have like 2 years worth of work to do. And so whatever you see over here is, I'm not trying to think much of it right now because again, this is just the preliminary run. And so I basically just took the initial mass and composition from one of the groups. And then just for starters, to test the waters, I used a small nuclear network and strand splitting, which is what other people are using. This is what the merger looks like. So this is a run that I did on Perlmutter using 512 CPU nodes because unfortunately my entire group uses GPUs and we ran out of our allocation pretty quickly. So someone had to make use of the CPU nodes and that was me. Again, just to test the waters, this is a preliminary run, 512 CPU nodes. And so I'll talk about what happens in the end. This 512 CPU nodes, and this cost me 8,000 CPU hours. And I think we are left with like another 4,000 CPU hours on Perlmutter, which I'll probably run through pretty quickly. But we just submitted a proposal to renew our allocation, so hopefully we'll get more time. So like I said, this is just a preliminary run. This is a very low resolution run. So this is 50 kilometers, and an average White Dwarf is like 6,000 to 7,000 kilometer at least. And so this is a very coarse grid. And in this case, we do get the double detonations. So this is just a snapshot of what happens. This is close to 114 seconds. And so this is the surface detonation, which basically triggers a carbon detonation inside the core. Again, we're not really thinking much of it because it's low resolution, small network, strand splitting. Ultimately, the goal for me is to get to a point where we have super high resolution. We use SDC like that because that's the integration method that we use. And we also want to explore bigger networks. So, and it's fun. And the funny part is that I use the same configuration on Frontier, which is OLCF, with 25 kilometer resolution. So that's higher than the resolution over here, and I do not get a second detonation. So like I said, things are very, I honestly don't know what's going on right now. But yeah, this is the density. Oh, I should have mentioned. So this is the temperature profile of the two White Dwarfs, and this is the density profile. And then, like I said, so the other two groups, another key point to note is that both of the other two groups, even though they had conflicting results, they did agree on one thing, that we do need really high resolution in order to actually resolve what happens inside the core. And so we do think that because Castro can be run fully on GPUs, we do think that those high resolutions are achievable with our code, provided they can give us more allocation. So I think, yeah, that's pretty much it. And then unfortunately, I don't have a scaling from Perlmutter because nobody let me run on GPUs. This is the scaling for this particular problem on Frontier. I just put it over here just for fun, I guess. And this basically means, so as we keep on increasing the number of cells, our resolution also keeps increasing. And so we can see that it is able to scale, I guess, decently well, or the best we can do. And then this is a plot of just analysis. This is just the thermodynamics looking at the temperature. This is a quick check to make sure that there is in fact a detonation and it's not just like burning away its material. And so over here we can see that from 1 billion Kelvin, we literally go to like 2 billion Kelvin. And that's just a way to check that it does detonate. I think that's all.
Don't remove your slides, leave them.
forgot, yeah.
Any questions?
Oh, yeah, sorry.
A question about time, actually both length scale and time scale. So like when in these simulations, like obviously these matter, but like it's not unfolding over seconds, right? Like this is how fast does this process happen?
So over
your
here-
simulation, is this like an approximation? Like, does it approximate reality?
So over here in this videos, what you're seeing,
Those are time steps, not, S is not seconds, right?
no, that is
It
seconds.
is, this happens
This is, this is simulation time.
Yeah.
It takes millions and millions of years for a star to go from being a main sequence and a red giant to finally a White Dwarf star. But then once it starts accreting, this can happen in like seconds. Yeah, so that is actual simulation time. And so like to get to those 115 seconds in simulation time cost me 8,000 CPU node hours. So, and because this is a 3D run, so naturally it's like super expensive. So yeah.
I have a really quick question. And then Roland's gonna ask a really expert question because he's a supernova person. The scaling plot that you had on Frontier, do you know like was it, like, do you know if there was the secondary detonation on some of them? Because you said the
So-
resolution is increasing, right?
Yeah,
Okay.
so in this case, we just ran it up to like 0.2 seconds of simulation time.
Okay,
And this was like no output, nothing. We just wanted to see how it scales.
Okay.
So this was purely just for like scaling purposes.
it'd be super interesting to see like second,
Yeah.
no second,
Yeah.
second, no second, like what's happening.
I think at this point you get up to like 5 kilometer in resolution, so which is really good. I'm hoping I can get to that, but we'll see. I'm currently facing a lot of issues with like running this problem because this was strand splitting. That's like super straightforward, super easy. We've already tested our setup with strand splitting, so it runs. But right now I'm trying to run it with SDC and I'm getting into a lot of trouble. And so I essentially haven't run anything for the last 1 month, unfortunately.
Okay, Roland.
In the studies where the detonation actually happens, what happens to the secondary?
So that's a good question. One of the groups is actually, so this group Parkmore et al., I don't know why it keeps doing that. Parkmore et al., so they came, I think it was in 2021, that they first did the study. Over there, they don't see a second detonation on its own, so it's not self-consistent. They manually put a second detonation over there just to see what would happen. And the funny thing is that this is a big problem in our community, but they don't talk about how it detonates. And then in 2022, they just suddenly have the second detonation, but again, they don't comment on it. They're more focused on the fate of the primary. There is, in theory, you could see 4 detonations. So as your primary explodes through the second detonation, it will send reverse shock waves into the secondary that can lead to a surface detonation on the secondary that will lead to a carbon detonation inside the secondary. So that's called, I don't know if it has a word, maybe like quadruple detonation. But that'll be fun to see.
But that would be like a way to maybe make a whole bunch more nickel or. You might
Absolutely,
be able to account for like things like super Chandrasekhar.
absolutely, absolutely, that's true.
Any other questions? Thank you so much. If you haven't already, if you want, you can use your phone to, I don't know if I can move that from here.
It should work.
I don't know, but I don't even know what to move. Well, okay, I'll put the link, maybe,
I don't
do you know how
see
to move it?
No, it's not blocked on my screen. Yeah, people in the room.
Oh, yeah, excellent.
There we go.
Yeah, so you can use your phone if you want, but I will also, you also got the link in your email for the survey. So you just do that now, then you won't have to do it later. And that will be really helpful for me in planning for the meeting next year. And I hope you come back and please take any food that's left. If you see Celeste, she's the one who organized all the food and coffee and the rooms and took care of everything that I could not take care of. So if you see her, please give her a big thank you as well. And enjoy the rest of your time here in the Bay. Thanks so much.